Here are several code violations related to an 800 amp service entrance with an automatic transfer switch. Code section 300.20 states that conductors entering a switchboard shall be protected by an approved terminal enclosure. The terminal enclosure for each set of conductors shall be designed for the number of conductors accommodated and the size of the largest conductor. Code section 300.20c states that conductors entering a switchboard shall maintain their ampacity through the switchboard. The arrangement of the switchboard shall be such that the required ampacity of the conductors can be determined without subtracting from the ampacity to provide for losses in the switchboard. Additional codes to consider include 300.4b, which mandates that neutral conductors shall have the same ampacity as the ungrounded conductors. Also, Code section 250.148 concerning the equipment grounding conductor requires it to have an ampacity not less than 1/3 the ampacity of the circuit conductors. The use of 4 nipples with the conductors specified creates several problems. Firstly, consider the ampacity issue. The 500 cm neutral conductor does not have sufficient ampacity to handle the current drawn by the 800 amp load. Secondly, there is the terminal enclosure issue. The terminal enclosure for the 500 cm neutral conductor is not designed for the number of conductors and the size of the largest conductor. Thirdly, we have the grounding issue. The number 2 ground is not an appropriately sized grounding conductor for an 800 amp circuit. To correct these violations and comply with code requirements, the following is recommended. Use 2 4-inch nipples, each containing 4 600 cm conductors and 1 1/0 ground. Let's elaborate on these points, starting with the ampacity requirements. In an 800 amp system, the neutral conductor must be able to handle the maximum neutral current that could potentially flow. The neutral current is influenced by unbalanced loads and harmonic currents. Code section 220.61 provides guidance on calculating neutral loads for feeders and services. It's essential to perform these calculations accurately to determine the minimum required ampacity of the neutral conductor. The 500 cm conductor may be insufficient, especially if there are significant nonlinear loads present, which generate harmonic currents. Using a neutral conductor with adequate ampacity prevents overheating and ensures the safe and reliable operation of the electrical system. Now, let's discuss the terminal enclosure requirements outlined in Code Section 300.20. This code emphasizes the importance of properly protecting conductors entering a switchboard. The terminal enclosure must be designed to accommodate the number of conductors and their size, providing a secure and insulated environment. The enclosure should prevent accidental contact with live conductors and protect them from physical damage. Using an incorrectly sized or inadequate terminal enclosure can lead to insulation breakdown, short circuits, and potential safety hazards. It's crucial to select enclosures that are specifically designed for the conductors being used and that meet all applicable standards and certifications. Next, consider the equipment grounding conductor as specified in Code Section 250.148. This conductor provides a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices such as circuit breakers and fuses. The equipment grounding conductor must be sized appropriately to handle the maximum fault current that could occur in the circuit. The code specifies that the equipment grounding conductor shall have an ampacity not less than 1/3 the ampacity of the circuit conductors. In an 800 amp system, a number 2 ground is inadequate to handle the potential fault current. A larger grounding conductor, such as a 1/0, is necessary to ensure effective grounding and minimize the risk of electrical shock. Remember to consult Code Section 250.122 for specific requirements on equipment grounding conductor sizing. Now, consider the recommendation to use 2 4-inch nipples, each containing 4 600 cm conductors and 1 1/0 ground. This configuration addresses the previously mentioned code violations and provides a safe and compliant installation. Using 2 nipples allows for better separation of conductors and reduces the potential for overheating due to proximity effects. The 600 cm conductors provide sufficient opacity for the 800 amp load, while the 1/0 ground ensures adequate grounding protection. When installing conductors in nipples or conduits, it's essential to follow the fill requirements specified in Chapter 9 of the National Electrical Code. These requirements limit the number of conductors that can be installed in a conduit based on the conduit's size and the conductor's cross-sectional area. Exceeding the fill limits can lead to overheating and insulation damage. Additionally, ensure that the conductors are properly supported and secured within the nipples to prevent strain on the connections. Also, consider voltage drop calculations to ensure that the voltage at the load remains within acceptable limits. Voltage drop can occur due to the resistance of the conductors, especially over long distances. The code recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. If the voltage drop exceeds these limits, it may be necessary to increase the size of the conductors or take other measures to reduce the voltage drop. Now we can also think about short circuit current rating. The automatic transfer switch and all other components in the system must have a short circuit current rating adequate for the available fault current at their terminals. The available fault current depends on the utility supply and the impedance of the service conductors. Performing a short circuit study is essential to determine the available fault current and ensure that all components are properly rated. Using components with inadequate short circuit current ratings can lead to catastrophic failure during a fault, posing a significant safety hazard. Also, think about coordination and selective coordination. The overcurrent protective devices in the system, such as the main breaker and any downstream breakers, should be selectively coordinated to minimize the extent of an outage during a fault. Selective coordination means that only the overcurrent device closest to the fault should trip, while other upstream devices remain closed. This requires careful selection and setting of the overcurrent devices, taking into account their time current characteristics. Lack of coordination can result in widespread outages and unnecessary downtime. Remember, arc flash hazard analysis is crucial for personnel safety. An arc flash is a dangerous electrical explosion that can occur during a fault. Arc flash hazard analysis involves calculating the incident energy and determining the appropriate personal protective equipment needed to protect workers from arc flash hazards. The results of the arc flash hazard analysis should be documented on warning labels affixed to the electrical equipment. Workers should be trained on the hazards of arc flash and the proper use of personal protective equipment. Let's also consider the labeling requirements. All electrical equipment must be properly labeled to identify its purpose, voltage, and other important information. The label should be durable and legible, and they should comply with the requirements of the National Electrical Code and other applicable standards. Proper labeling helps prevent confusion and ensures that workers can safely operate and maintain the equipment. Then consider the accessibility. Electrical equipment must be readily accessible for inspection, maintenance, and repair. The code specifies minimum clearances around electrical equipment to provide adequate working space. Obstructions that block access to electrical equipment can create safety hazards and hinder maintenance efforts. Also, think about the environmental conditions. The electrical equipment must be suitable for the environmental conditions in which it is installed. This includes temperature, humidity, and exposure to corrosive substances. Equipment installed in harsh environments may require special enclosures or other protective measures to prevent damage and ensure reliable operation. After that, consider the surge protection. Surge protection devices should be installed to protect sensitive electronic equipment from voltage surges caused by lightning or other transient events. Surge protection devices divert excess voltage to ground, preventing it from damaging the equipment. The code requires surge protection in certain applications, such as dwelling units and critical facilities. Also, there is the harmonics mitigation. Harmonic currents can cause overheating of conductors and equipment, as well as interference with electronic devices. If harmonic currents are present, it may be necessary to install harmonic filters to mitigate their effects. Harmonic filters reduce the amplitude of harmonic currents, improving the power quality and preventing equipment damage. Think about energy efficiency. Energy-efficient electrical equipment should be used whenever possible to reduce energy consumption and lower operating costs. This includes energy-efficient motors, lighting, and transformers. The code contains requirements for energy efficiency, such as minimum efficiency standards for certain types of equipment. And there is the maintenance and testing. Regular maintenance and testing of electrical equipment are essential to ensure its continued safe and reliable operation. This includes inspecting connections, testing insulation resistance, and calibrating overcurrent protective devices. A written maintenance and testing program should be established and followed to prevent equipment failures and safety hazards. Consider any local codes and regulations. In addition to the National Electrical Code, there may be local codes and regulations that apply to electrical installations. It's essential to be familiar with these local requirements and ensure that the installation complies with all applicable codes and regulations. Also, hire qualified personnel. Electrical work should be performed only by qualified and licensed electricians who are familiar with the National Electrical Code and other applicable standards. Using unqualified personnel can result in substandard installations and safety hazards. A licensed electrician has the knowledge and experience necessary to perform electrical work safely and correctly. Permits and inspections may be required. Depending on the jurisdiction, a permit may be required before starting electrical work. The work may also be subject to inspection by a code official to ensure that it complies with the applicable codes and regulations. Obtaining the necessary permits and inspections helps ensure that the electrical installation is safe and code compliant, and documentation is essential. Maintain accurate documentation of the electrical installation, including wiring diagrams, equipment specifications, and test results. This documentation can be valuable for troubleshooting problems, performing maintenance, and making future modifications to the electrical system. Proper documentation helps ensure the long-term reliability and safety of the electrical installation. Remember that ongoing training is required to stay up to date on the latest codes and technologies. The electrical industry is constantly evolving, with new codes and technologies being introduced regularly. It's essential to participate in ongoing training to stay informed and maintain your skills. Staying up to date on the latest developments helps you provide safe and efficient electrical services. So, consider conductor directing. When multiple current-carrying conductors are installed in the same conduit or cable, their ampacity must be derated to account for the increased heat generated. The code specifies derating factors based on the number of conductors and the ambient temperature. Failure to derate conductors can lead to overheating and insulation damage. Also, consider the neutral sizing in a three-phase system. In a three-phase system with nonlinear loads, the neutral conductor may carry more current than the phase conductors due to harmonic currents. The code requires the neutral conductor to be sized to carry the maximum neutral current that could potentially flow. This may require increasing the size of the neutral conductor compared to the phase conductors. Also, think about the grounding electrode system. A properly installed grounding electrode system is essential for providing a low impedance path for fault current to return to the source. The grounding electrode system typically consists of a ground rod, ground plate, or underground metallic water pipe. The code specifies the requirements for grounding electrode systems, including the size and type of grounding electrodes, as well as the bonding requirements. Also, the equipment bonding jumpers should be installed. Equipment bonding jumpers are used to connect metal enclosures, raceways, and other non-current carrying metal parts to the grounding system. This ensures that these metal parts are at the same potential as the grounding system, minimizing the risk of electrical shock. The code specifies the requirements for equipment bonding jumpers, including their size and installation methods. Think about the separation of power and data cables. Power cables and data cables should be separated to prevent electromagnetic interference. The code specifies minimum separation distances between power and data cables. If it is not possible to maintain these separation distances, shielded cables or other mitigation measures may be required. Also, there is the cable support. Cables must be properly supported to prevent strain on the connections and to protect them from physical damage. The code specifies the requirements for cable support, including the type and spacing of cable supports. Improper cable support can lead to cable sag, insulation damage, and potential safety hazards. Then consider the conduit fill. The code limits the number of conductors that can be installed in a conduit based on the conduit size and the conductor's cross-sectional area. Exceeding the conduit fill limits can lead to overheating and insulation damage. The code provides tables that specify the maximum number of conductors allowed in different sizes of conduit. Now, there is also the box fill. The code limits the number of conductors, devices, and fittings that can be installed in an electrical box based on the box's size. Exceeding the box fill limits can make it difficult to make connections and can lead to overheating. The code provides tables that specify the maximum number of conductors, devices, and fittings allowed in different sizes of boxes. In addition, consider the protection against physical damage. Cables and conductors must be protected from physical damage. This can be accomplished by installing them in conduit, raceway, or other protective enclosures. The code specifies the requirements for protection against physical damage, including the types of enclosures that are permitted in different locations. Also, there is access to overcurrent devices. Overcurrent devices, such as circuit breakers and fuses, must be readily accessible for inspection, maintenance, and replacement. The code specifies the requirements for access to overcurrent devices, including the maximum height at which they can be installed. Improper access to overcurrent devices can make it difficult to restore power after a fault and can create safety hazards. Then consider the working clearances. Adequate working clearances must be maintained around electrical equipment to provide a safe working space for electricians. The code specifies the minimum working clearances required for different types of electrical equipment. Obstructed working clearances can make it difficult to perform maintenance and repairs and can create safety hazards. And there is the identification of disconnecting means. Each disconnecting means, such as a circuit breaker or switch, must be clearly labeled to indicate the equipment it serves. This helps prevent accidental disconnection of critical equipment during maintenance or repairs. The code specifies the requirements for identification of disconnecting means, including the type and size of labels that are required. Also, consider the guarding of live parts. Live parts of electrical equipment must be guarded to prevent accidental contact. This can be accomplished by installing enclosures, barriers, or other protective measures. The code specifies the requirements for guarding of live parts, including the minimum height at which live parts must be guarded. Finally, consider the use of approved equipment. All electrical equipment must be approved by a recognized testing laboratory, such as Underwriters Laboratories or Intertek. Approved equipment has been tested and found to be safe for its intended use. Using unapproved equipment can create safety hazards and may violate the code.